In this video, we're going to see how we can calculate the expectation of a continuous random variable. And to illustrate this, let's consider an example. Suppose that an alien race lands on the planet Earth. Now, this race is very unusual because the heights in their population are distributed following a uniform distribution. In this case, it's a uniform distribution between 170 centimeters and 190 centimeters. So that is the probability density function Fy of y is given as 0 for y less than 170 centimeters. That means that you'll get no one whose height is less than 170 centimeters. It's 0 for y greater than 190 centimeters. Then it's constant between 170 and 190. And in order to make sure that the area under the curve is equal to 1, the height of the probability density function needs to be equal to 1 over the width of that non-zero area. So in this case, the width is 20 centimeters. So in order to make sure this entire area is equal to 1, the height must be equal to 1 over 20. Now the question is, how do we go about calculating the expectation? We know that for a discrete random variable, let's say x, the expectation of that discrete random variable would be equal to the sum over all possible values of x of the probability of each possible outcome multiplied by that outcome. But this is not a discrete random variable, this is a continuous random variable, and so we can't write down the probability of any given outcome, because the probability of any given outcome is just going to be equal to 0. But we do know our probability density function and all of the possible outcomes. Now, when we've got a continuous random variable, rather than adding up those products, we're going to need to use a continuous equivalent, which is to integrate the product of the probability density function with the outcomes. So in this case, the expectation of y, or the average height within the population, is going to be equal to the integral over all possible values of y of our probability density function times by each of the possible outcomes of y, and we integrate with relation to y. Now, we've got three sections to this integral. We've got the section where the probability density function is 0 between minus infinity and 170 centimeters. We've got the section where it's non-zero between 170 and 190 centimeters, and we've got the section where it's 0 again for y greater than 190 centimeters. So we can write this down as three separate integrals. So we can write down the integral between minus infinity and 170 of the probability density function, which is 0 times by y dy, plus the integral between 170 and 190 centimeters of the probability density function, which is just equal to 1/20th here. So that's 1/20th times by y dy, and then the integral between 190 and infinity of 0 times by y dy. Now, the bits where the probability density function which are 0 are not really interesting, because this integral and this integral is just going to be equal to 0. So we can get rid of that and that, leaving us with the expectation is just equal to the integral between 170 and 190 of y over 20 dy. Now, this is a relatively straightforward integral. Because we've just got a simple y here, we can raise the power of y by 1 and divide through by the new power. So this is going to be equal to y squared over 2 times 20, or y squared over 40, and we'll evaluate that between 190 and 170. Substituting in our values for the limits, 190 and 170, we get this is equal to 190 squared minus 170 squared divided through by 40, which is equal to 7,200 over 40, or 180 centimetres. Now, this shouldn't be too much of a surprise, because for any uniform distribution, the average is just going to be in the middle of the distribution. So here we've got our uniform distribution, and you can see that the middle value is just equal to 180 centimetres. If we were to plot a line right in the middle of this rectangle, we can see that that is equal to 180 centimetres. The middle point of this uniform distribution, where you have 50% of the outcomes to the left and 50% of the outcomes to the right, lies right in the middle of the distribution, which for the uniform distribution will also be equal to the expected value. So in this video, we've seen that to calculate the expected value of any continuous random variable, we can do that by integrating the product of the probability density function with all of the possible outcomes of y, and that will give us the expected value. And for a uniform distribution, that will be in the middle of the distribution.